Yeah, good morning all of you. My screen is visible.
Yes, sir.
Okay. We'll see the continuation of previous class. I already explained the classifications of phase control rectifier, and one of the example I gave half-wave rectifier, and then we'll move on to that for the rest of the controllers. So these are the classifications I mentioned. Single phase and three phase, again half wave and full wave, similarly for three phase also. This we discussed already, just I am reviewing that. And full wave again we divided as a midpoint converter and bridge converter, and bridge converter dividing as a semi converter and full converter. So these are the complete third unit. It is related to phase controlled rectifier. All the controllers, it will convert fixed AC to the variable DC. So these are all whatever we can use it. So it will do fixed AC to the variable DC, and that depends on our requirement. We need to select the which controller is suitable for that particular application. Means based on the application we will select this. Suppose application required only motoring operation, then you can use as a semi converter. So if it required motoring and braking operation, then you go for as a full control rectifier. Suppose our load is a little bit high rating and motoring, you can use this, and both is required, you can use this. Like this, we may have a lot of controllers, subcontrollers, but the thing is, all these controllers we need to observe with different load conditions. So here the thing is, the load may be R load, because in our syllabus itself they mention different loads. So R load may be RL load, or maybe something RLE load, like this. So what we will do is, controller is any of the controller. It may be half or full or semi or anything. Let it be this one is a controller. That controller depends. And now this may connect to R load, or this may be connected to RL load, or maybe RLE load, like this. So what we will do is we will check the performance with different load conditions, and after that by variation of alpha only we are getting as a variable output voltage, and we are changing the alpha and we'll notice what is your response. So that is the complete third unit, phase control rectifiers. And now why this is preferred than conventional methods, that also one small example we'll see that. Because in normally, as I mentioned, no, in application, this is on to understand, we'll replace this to something different loads, no. And after that in the real application, what we'll do is, this total loads are replaced by motor. This is our motor. So our motor, you need to check the performance, the speed of the motor. So here, controlling the speed, whether it is armature control or it may be flux control, so like that, or in the same setup I may be need both, that is above the rated speeds or below the rated speeds. So all these things performance we can analyze that. Preferably this concept will come into the dry subject. Just for understanding, I already explained this circuit. This is very quite simple. If any circuit you try to understand, how to get the output and operation of this. In any circuit there is a operation is two simple way. One is a during positive of cycle what will happen, that means this portion, and during negative of cycle what will happen, that's all the explanation. In this positive of cycle we need to explain one para, Negative off cycle we need to explain the other para, and then rest cycle is going to be repeated. So for this no need to explain any further, only we will write one sentence, cycle is going to be repeated. And here, and if you replace R by RL load or RLE load, all the things, the waveform will coming from this basic information only, or basic waveforms only. Further modification is going to be takes place. That's why any one circuit operation, if you know, the rest of the things are slight modification with comparison to this one. That is only the difference. That's why you no need to worry about the waveforms. Small waveform, if you understand, sequence of the procedure also same, and you need to understand, if I replace R load by RL load, what is the modification and why. Similarly, RL load is replaced by RLE load, what need to modify and why. So that's two simple steps. If you remember, we can easily draw any circuit waveforms by your own. Now always we'll start with the supply. We need to draw the supply, because this is the supply and this one is your load. So by operating this thyristor, how the load is going to be vary. That is only our requirement. Anyhow, this all the things will come back once again in the respective units. As I mentioned, for the lab purpose as well as your understanding purpose, I will cover all the controllers introduction and basic nature and all. So this is only for your brief introduction only. Again, everything will come back once again in the respective units. That you keep it in mind. That is the reason I try to explain the controller operation and for the relevant to the lab purpose. That's why anyhow I need to cover all the things to know your subject. That's why I started in theory part, and once you aware the controllers, then I will start the lab, the experiment wise, and there also I will explain in detail of that circuit, operation, derivation, waveforms, then how to connect through simulation software. So all the things will come in the lab also. Once again it will come into the lab. Now I draw the supply. As usual, as you know that any one full cycle also sufficient. I draw the supply. Supply start with 0, pi, 2 pi, 3 pi and so on. This is a fixed throughout this unit. And later I have to represent the pulses, firing pulses. Why firing pulses are required? To fire the device at your desired instant, must and should I have to provide the firing pulse. That's why this I need to provide. So how many pulse for positive off cycle only? This is a forward bias. That's why wherever positive off cycle is there, you need to provide the firing pulse at an angle of alpha. No need to provide only this instant. You can start this instant also, but whenever you want to fire the device, there you have to provide the pulse. Or still I want to wait some more time because I want only less voltage, then you can give firing pulse here. Or still you can increase the alpha. Like this, wherever you want to provide the pulse or wherever you want to fire the device, at that instant need to provide the firing pulses only for positive off cycle, because for negative off cycle thyristor is a reverse bias. Even if you give the pulse also it won't conduct. That's why generally we don't provide the firing pulse for negative off cycle if it is only one thyristor. Suppose some other thyristor is there in full wave rectifier, that thyristor is forward bias during negative off cycle, then you can provide one more pulse like this for negative off cycle at the same alpha. So whatever alpha you provide, if you want to change, you can change here also and here also. So this is the firing pulse for negative off cycle. So this is the Ig2. Whenever if you have the Ig2 in second thyristor in the circuit, That too, full wave rectifier, this will be forward bias during positive half cycle. This will be forward bias during the negative half cycle. So that is the difference for half wave rectifier and full wave rectifier. Firing pulse we need to provide additionally during negative half cycle. So like that, small changes only is required while you are drawing the waveforms. Now after this, what I want to do, I want to represent output voltage waveform. Explanation is very simple. During positive half cycle from 0 to pi, thyristor is a forward bias. That is the first statement. Then second statement, at an angle of alpha means omega t is equal to some angle or alpha may be 30 degrees, 20 degrees, 10 degrees or 90, whatever you want from 0 to 180 degrees. At an angle of alpha that is equal to 30 degrees or anything in simple sentence, at an angle of alpha, firing pulse is given to the thyristor. That is the second point. Once firing pulse is given to the thyristor starts conducting. Third point. And once thyristor is conducting, output voltage is same as the source voltage because current is passing from phase thyristor or it goes to the neutral. Then load is directly connected to the source. Output voltage same as the source voltage. What is the source voltage? This is the our source voltage Vm sin omega t. Same thing, we'll get it in the output at an angle of alpha only. Before alpha, what will happen? Before alpha, thyristor is forward bias, but it is not conducting. That's why output voltage is 0 before alpha. Means from 0 to alpha, output voltage is this one will be 0. At an angle of alpha only, we are providing pulse to the thyristor. That's why we are getting same as the source voltage. This is the same as the source voltage will obtain. This is a pi. Alpha to pi will get same as source. That's all the output voltage. Now I want to draw the current. How will you draw the current? Here load is a resistive load. That's why source voltage and load current are in voltage and current are in phase. That's why you can draw the load current waveform same as the voltage waveform with reducing magnitude. So this is a current waveform. So exactly voltage and current waveforms are same except magnitude. And now if I want to draw the voltage across the device, means voltage across the thyristor, and here as you are aware that when the switch is open, what is across the switch? Same as the source voltage. It is connected like this, no? If device is off state, same as the source voltage. If device is closed, means thyristor is closed, then it is a short circuit. Voltage across that will be 0 or 1 to 1.5 volts. It is a very less voltage. Drop across that will represent voltage across the thyristor. Or simplicity, whenever thyristor is on, voltage is 0. Across voltage I am telling. Whenever thyristor is open, voltage across the device same as the source voltage. Now, as you are aware that 0 to alpha, thyristor is off state. That's why output voltage is 0. But what about the voltage across the device same as the source? What is the source? It is a source. See this one. So now we simply redraw that up to alpha. From alpha onwards, what will happen? Thyristor is conducting. So output voltage is getting, current is getting, but voltage across the device is 0. This you can represent 0. This is what How long it will be conducting? Up to pi. Once pi reaches, due to natural commutation, thyristor is open. Once if it is open, out voltage across the thyristor same as the source voltage. So now source is what? From pi onwards it is a negative. How long it will be same? Until if it conducts. So it is conducting only at 2 pi plus alpha. Up to that we can represent same as the this voltage in the across the voltage. So now this portion is 0, anyhow it is open. All the cycle is going to be repeated from this point onwards. This 2 pi onwards cycle is going to be repeated. Again this will be on and current also will be start and this will be turn off like this. Cycle exactly this portion is repeated here. So that much simple. Now if you have any doubt you ask me. It is very simple. 2 steps. When thyristor is on, voltage, load voltage same as the source, current also same as the source or voltage waveform but reduced magnitude because of the resistor. And at an angle of phi it is going to be open. If it going to be open, voltage will be 0 and voltage across the device is just reverse of this. Or one way you can remember, very small logic. If switch is on, switch is off. If this is on and off condition, I want to know what is the output voltage, what is the voltage across the device. This is the simple table. If you remember, this table is required throughout the unit. When switch is on, because it is a thyristor, thyristor is on, output voltage same as the source. What about this? Voltage across the thyristor, if it is on 0 and you come to the switch is open, output voltage will be 0 and across this will be same as the source. That's all. You remember this table. You can easily draw your waveform. Same waveforms you can see at this instant. You identify when a switch is on, when a switch is off, all the things. So this is the brief introduction when if you use as a thyristor. Now we will see the same thing, waveforms. Just like this you can draw the waveforms. This is a voltage across the device. Now the derivation is very simple. Any derivation, especially for power electronics, if I want to know average output voltage, what you will do is just take it full cycle and integrate it. I want average output voltage. Let's see how to derive this average output voltage. How will you get the average voltage? One full cycle you have to integrate it. That's all. From where to where one full cycle? You can see this from 0 to pi, one half cycle. Pi to 2 pi is another half cycle. So that means you need to integrate this one full cycle from here to here is a one full cycle. Output voltage I want to know. In output waveform, you just integrate. You don't want to see whether it is half wave rectifier or a full wave rectifier or a semi converter or a full converter or a single phase or a three phase. Irrespective of the any controller, that controller output voltage waveform you integrate one full cycle. That's it. So one full cycle means average I want to know 1 by 2 pi, one full cycle, and I have to integrate. What is the integration limit? See that this is 0 to alpha, output voltage is 0. That's why anyhow integration also 0. From alpha to pi means integration alpha to pi. What is your output here? This is same as the input. What is input? Vm sin omega t. So integrate alpha to pi Vm sin omega t d omega t. plus what next up to 2 pi, no? From pi to 2 pi, what will happen? Output is 0. So no need to do. So initially from 0 to alpha, output is 0 plus alpha to pi Vm sin omega t plus pi to 2 pi 0. So you just integrate only this. Then what I can get? Vm is a constant outside. Vm by 2 pi integral sign will give minus cos omega t. Limits are alpha to pi. Then we substitute that, what I can get? Vm by 2 pi cos pi minus 1, already minus is there 1, and plus cos alpha. Cos alpha. That's all. So this is your average output voltage. Now the question is whether this phase control rectifier will give variable output voltage or not. That is the question. Whereas diode rectifier, it won't be variable one, it is a fixed one. That also I will explain. At moment, this is a phase control rectifier. Which one is a variable parameter in this? Alpha is a variable parameter because Vm is fixed. What is Vm? Peak magnitude? No. This is root 2 into Vs, that is a Vm. 2 pi is constant, 1 is constant plus cos alpha. Variable parameter is a alpha. So if I give alpha is this, you will get one output. You can give here, you can get one output, or you can give here, you can get another output. Like that, alpha varies, you can get output voltage variable 1. Now if I put alpha is equal to 0, cos 0 is 1, 1 plus 1 2. So that 2 and here denominator 2 will get cancelled. Your output will be Vm by pi. And now if you keep alpha is equal to 30 degrees, cos 30 plus 1 and Vm by 2 pi. And if I give alpha is equal to 90 degrees, so cos 90 0. So output will be Vm by 2 pi. And if I give alpha is equal to 180 degrees, cos 180 minus 1 plus 1 minus 1 get cancelled 0. So that will be 0. So now we can see the variation. If I keep alpha is 0, I will get Vm by pi. If I keep alpha is equal to 90 degrees, I will get Vm by 2 pi. Similarly, if I use 180 zeros, that means is it variable or constant? So it is going to vary with respect to alpha. And also we can observe that alpha increasing, then output voltage is decreasing. Alpha is small or a 0, you will get Vm by pi. Then I increase to 90, half of that only I am getting. Still if I increase to 180, 0 I am getting. That means starting will be more and gradually it is decreasing, finally reaches to the 0. So this is the waveform nature with respect to alpha. 0 will get maximum, 90 degrees will get half of that, and 180 degrees will reaches to 0. This is a 180 degrees. So like that, so this is the, from this I can say it is a variable one. If it is a diode rectifier, what is our output? It is started like this, no? And there also integrate one full cycle. What is the limits now? Instead of alpha, you put it 0, 0 to pi. Then you integrate this, what I can get? V out is equal to, for diode rectifier, Vm by pi. If I integrate that 0 to pi, I will get output voltage is Vm by pi. Whereas here, I will get Vm by 2 pi into 1 plus cos alpha, and this is a Vm by pi. Here no variable parameter. This one is a fixed one. This one is a variable one. So this is the difference between diode rectifier and phase control rectifier. That's what I mentioned here in the derivation also. See that 0 to 2 pi I need to integrate, and then the limits are only alpha to pi, rest portion is 0. If I do that, Vm by 2 pi into 1 plus cos alpha. Similarly, if I use the diode rectifier, I can get Vm by pi. That's the reason this is a variable one, this is a fixed one. And now why we required this type of controllers in application side? As in the conventional method, this is a speed control of a DC motor. What controller? It is a armature controller. So how will you get the variable speed here? By controlling the rheostat is connected in series with the armature. We are adding the resistance and increasing the resistance here. You can able to control the speed that is a below the rated speed by exciting the field 1 total voltage, and here you can change that resistance in the field winding side. RA is armature resistance, whatever winding resistance. In addition to that, we added additional resistance. Then what will happen? Suppose if I add 10 ohms additionally, existing plus 10 ohms, what will happen? Total resistance will be more. If resistance is more, then automatically voltage drop will be takes place at this side. Rest of the voltage only passes through the armature winding. So voltage is decreases, speed also going to be decreases. So that is if by controlling here, you can able to control your speed. So similarly, still if you add more resistance, then speed further decreases. And what is the maximum speed I can get here? You remove complete this rheostat, maximum will get same as the normal speed, rated speed. This will get direct voltage because no resistor, no direct voltage applied across the armature terminals, will get it as a rated speed. From this one notice is, by adding the resistance, speed is going to be decreases, and if you add more and more resistance, you won't pass any voltage because everything goes to drop, and then speed will be nearly 0. And the maximum speed is, if you disconnect this rheostat, rated voltage will applied across the machine, you will get the rated speed. That is the reason we can say it is a below the rated speed. But what is the drawback here? By using the resistor, you are controlling the speed, then power dissipation is going to be drop down. So this is a power dissipation takes place. That is the if we are operating as a high machines, lot of power is going to be dissipated. So that is the drawback. And now the same thing logic, N is directly proportional to EV by phi. EV is nothing but V minus IA RA. Then V is fixed one because apply voltage is fixed one, and RA plus something you add the resistor here, then this drop, this portion, negative portion is reduced, means the drop will be increased, and fixed minus this increasing portion, the resultant will be decreased. That is directly proportional to the speed. Let shunt motor flux is constant. So what will happen? Speed will be decreased. This is the conventional method. How this going to be replaced by our phase control rectifier? What is the difference and how it will be benefited? This is the characteristics: normal speed, rated speed, and you are adding the resistance, speed will be gradually decreases. This is the characteristic. Now similarly for field or flux control also possible. We are keeping armature voltage is maintained constant, and the field current pass through the field winding is varies by using the resistance. Then automatically what will happen? Flux will be decreases, current will be decreases, and current and speed will be inversely proportionate. So this is the formula. What you can see is we are adding the resistance in the field side. By adding the resistance in the field winding, current pass through this field winding will be decreases. Once current is decreased, then automatically speed will be increases. For that, N is directly proportional to EB by phi, I told no. Now here I am giving as a rated voltage, EB is constant, and then flux is inversely proportional to the speed. So whenever current pass through the winding, field winding is changed, or let it be you are adding the resistance, then current will be minimum. then flux will be minimum. So if denominator is minimum, so automatically what will happen? If this is a minimum, then speed will be high. With that logic, you are keep on reducing the current pass through the field winding, you will get it as a higher speed. So these are the two things are already available conventionally, what we are doing in the laboratory. This is the characteristics. Now, how these things is replaced by our controller. One thing you remember for armature voltage is going to be controlled. Another one, field current will be controllable one. Yeah, voltage control, current also will control. So these two things you can apply using our phase control rectifier. So this is a motor RA, LA and EV or RLE, equivalent circuit of a motor is like this will represent. So now I want to control armature as well as the field. For that I am using as a one phase control rectifier. All the circuits will come back again. Only for difference I am telling. What benefit if you use as a phase control rectifier? Instead of rheostats, directly I am using as a phase control rectifier. By controlling this alpha, for this controller alpha, if I am changing, what will happen? Here voltage is going to be controlled. If voltage is controlled, what will happen? Speed is going to be controlled. Without using any rheostats, you are simply vary the alpha. It is a small knob. By varying the alpha, you are getting as a variable voltage and variable speed. Voltage is directly proportional to the speed. Similarly, for field control, whereas while you are doing this control, you keep this voltage will be rated voltage because alpha keep it 0 and automatically higher voltage will be obtained. If I keep alpha is 0 in this side, field side alpha is 0, you will get as a rated voltage, field will be excited and change that this side armature side alpha, then what will happen? You can keep on changing 0, 30 and so on. Automatically you are controlling. Other version what you have to do, you keep this is a fixed one, rated voltage if you apply, mean let it be alpha is 0 and you vary this field 30 and so on. Then what will happen? Voltage will be decreases, current will be decreases. If current is decreases, speed will be increased. Like this, very simple way you can able to use the phase control rectifier to control the speed of a motor, whether it is above the rated speed or below the rated speed, by make use of the phase control rectifier to control the speed of a DC motor, whether it is a series motor or separately excited motor. This is a separately excited motor. Like that, all that characteristics will come under drive subject. Any of that in the other semester. This is the advantage. Just one advantage I explained simply. And now we'll move on to next one. Next controller. What is the next controller? Chopper. So what is the function of chopper? As you are aware that like a phase control rectifier, here also another controller. There we will have fixed AC to the variable DC. Now chopper function is a fixed DC to the variable DC. In the phase control rectifier, fixed AC to the variable DC and here fixed DC to the variable DC. Now that's one I wrote here. A DC chopper converts fixed DC input voltage to a controllable DC output voltage or a variable DC output voltage. This is the main function of a chopper. And this requires forced commutation to turn off the thyristor. This also I mentioned. Why forced commutation is required? Because to turn off the main switch, current pass through the device bring to the 0. In the DC supply, the current will never goes to 0 until unless if you apply forced commutation. That is the reason we need to use forced commutation to turn off the thyristor. And then for low power circuit, thyristors are replaced by transistors. In the switch, I told no, either switch may be SCR or a thyristor, or BJT, or MOSFET, or IGBT. Any switch you can use it. But for low rating applications, we can use BJT and MOSFET and all. For high rating application, preferably we'll use as a thyristor, very high rating application. So that's the reason. Another, there is a classification depends on the type of commutation and the direction of power flow. So anyhow here commutation is a forced commutation. So that's why the chopper, forced commutated chopper, or voltage commutated chopper, or current commutated chopper, like that we'll use the names. But depends on our direction of the current, we can divide the classification first quadrant chopper, two quadrant chopper, and four quadrant chopper. Like that, the choppers we can classify based on the direction of the current, and other classification also there based on whether it is a step up chopper or a step down chopper or up and down chopper, like that. That is the classification. There is a lot of applications in the choppers. One is a DC drives, and then electric cars, and trolley trucks, and then battery driven vehicles, all that's EVs and all. So all these type of application. And rectifier also will use DC drives only, but that whenever input is AC, you can use that rectifier, phase control rectifier. But here input is a DC, that's why we need to use chopper, DC to DC conversion purpose. So these are the some of the applications. And now conventionally you can see that how a variable DC voltage is going to be obtained. There is input is there DC voltage. I want output also will be as a DC. This also I want DC. How will you get the variable DC? Then by controlling the resistance, you can able to get it as a variable DC. If you measure the voltage across the load side, what will happen? By changing this resistance, suppose resistance is maximum, then what will happen? The current will pass like this, no? Whenever current is passing through the resistor, there is a IR drop is going to be takes place, and power loss also there, I square R loss. So whenever the drop is there, remaining voltage is across the load side, and we are reducing that resistance value, and finally you will get it as output is equal to input whenever resistance is very less or a zero level. So we are doing this mechanism is nothing but a potential divider. Resistor or a rheostat is connected in between the source and load, then this is your output. So you will get output will be like this. Then what will happen? You can able to control your output by doing this. But by doing this, I can get it as a variable DC voltage in the output side. But what is the drawback? Because variable DC voltage are getting in the output, but it is not above the source. Maximum I can get same as the source, and only it will give below the source only. So this way you can able to control the voltage by using as a resistance control method. Preferably we don't use this method, because to get variable voltage I am simply wasting the power because of the resistor. That's why generally this method won't be preferable one. And other method also there, motor generator setup. It is there in our lab also. So in our laboratory, one of the experiment is there to get variable voltage. That experiment name is a magnetizing characteristics of a DC generator, or OCC characteristics of a DC generator, or open circuit. So that experiment setup will give variable voltage from starting to rated value, but it is not possible to get beyond the rated. This is a characteristics, if you remember. So there is a EG, generated voltage of a generator, and then excitation of a generator. If I change the field current gradually, if I increase the field current, then what will happen? Generated voltage is going to be vary gradually. And if you are keep on varying this generated voltage, once if the core is saturated, again it is further, it won't be increases, it remains in the constant. From this, what we can notice, from near to the 0 to rated voltage, it is varying by varying as a field current, but it's not zero exactly. There is a some due to the residual magnetism. There is a small Eg will be there initially. From that point onwards, it is gradually increasing. Finally, it reaches to as a rated voltage. This is also variable mechanism. By changing the excitation of a generator, you will get it as a variable voltage. But what is the drawback in it? I need motor as well as the generator setup. So, but you cannot get beyond the rated voltage, and this motor loss, generator loss, and cost of that setup, and then floor area requirement. So all these things leads this method also not a suitable one to use as a variable. That's what I used a small circuit, motor and generator. So here motor not shown, you just coupled as a motor as a prime mover, or you can say that, and you can give the supply to this and it will run, then it is going to be generate the voltage. This is a characteristics. By changing the excitation, you can able to vary the output voltage. Once it reaches saturation, it will become as a constant. This is the another method, second method. And then third method, there is a AC link chopper. What we'll use is, you may use the combination of the controllers, you can get it as a variable voltage. For that, first inverter, what is the function of inverter? It will convert fixed DC to the variable AC. So use the inverter, you can get it as a variable AC. There is a link, AC link chopper, and use the diode rectifier, it will convert AC to the DC. And how this DC is going to be variable 1? Because by controlling the firing angle of a inverter, this AC is going to be varying. Suppose if alpha is equal to 0, then you will get one value of AC. Correspondingly, you will get one value of DC. Let it be alpha is equal to 0, you may get 230 volts, just for example. And here you may get DC voltage is 200 volts, assume. And alpha is equal to 30 degrees, you will get 200 volts here. And proportionately, you will get 180 volts here. And you change alpha to some 60 degrees, there is a 180 volts, then this may be 160, like that, just not exact values, there is a small by changing the alpha, you will get variable AC, and that AC is input to the diode rectifier, automatically output is going to be control 1. This is a another method is there to get variable DC, but here also there is a drawback. Our intention is to get only the variable voltage. For that, we are using as a inverter and diode rectifier. Two setups are required. This is also a little bit costly. That's why generally this method also not a preferable one. And finally, we are using as a chopper. It is a controllable switch. This operation is very simple, efficient, and then power losses are nearly zero. So that the reason all other above three methods will not be used for the any control purpose. Will use only the chopper. So now we can see this is a circuit. By seeing this, it is very simple. Only one controllable switch. That switch either maybe thyristor, BJT, MOSFET or IGBT, anything, it is a controllable one. And I used as a one box across the switch or in surrounded by that switch. Meaning is the total setup, I call it as a chopper, means switch. In addition to additional circuit is there inside. I don't want to show every time that forced commutation circuit. That box represent it consisting of a forced commutation circuit. Whenever you want to turn off, that forced commutation will act and device is going to be turned off by using forced commutation. So this total setup, I call it as a chopper. What it is doing here, suppose if I close the switch, how the switch is going to be closed? It is not a manual one. By giving firing pulse to this switch, automatically switch is going to be closed. So for that we need as a one firing pulse. Here instead of call it as a firing pulse, we call it as a duty ratio or delta. That is a duty ratio. The means here the delta will be vary by means of the control strategy. In that case, we required one control strategy to turn on the switch here. So that ratio we need to provide at any instant. Let us assume that range is 0 to 1. Duty ratio range is 0 to 1 or 0 to 100%. So using this, you can able to get that on position. So now switch is on. Then what is your output? Suppose input is 12 volts, your output also 12. First switch is on case and switch is off, then what is your output? How the switch is off? Internally in this box there is a forced commutation circuit is there. Using that forced commutation, you can able to turn off the switch. The switch is off means open, output voltage is 0. If you do that mechanism regularly, if I want to draw the waveform also simple, no? First input, what is input? Let it be input is a Vs, whatever may be magnitude. Let that may be 12 volts. This magnitude is 12 volts. And then I have to provide the firing pulses. The duration on period means just at this moment. On period means switch is going to be closed. Off period means switch will be open. Again on period means switch will be closed like this. This is a Ig pulse. And then according to this duration, this is on period. This is a off period. Now when switch is on, what is your output? Same as 12. You just draw the 12 volts output here. How long? Up to on period. And switch is off, output voltage is 0. Up to this it is 0. So now this is the case of on period and off period. This is only the output over. So now whether it is a variable or not, that's only we want to find. And this on period, this is off period, total output we are dividing like this. And as I said previously, to get the average, you need to integrate one full cycle. What is the full cycle here? On duration plus off duration, I call it as a one full cycle. T on plus T off, that is a T. T is equal to T on plus T off. So this we call it as a total time. And now I am integrating. Instead of 1 by 2 pi, you will 1 by T on plus off. What is the limits? This is 0. This is a T on period. And rest anyhow 0, no need. So 0 to T on. What is your output? What is your output? Same as input, no? When switch is on, see that switch is on, output is same as input. So what is input? Vs into dt. Then that is equal to, what I can write? Vs into T on by T. Output is equal to this one. So just for simplicity, V out is equal to Vs into this, I call it as a delta over T on by T is a ratio. That I call it as a duty ratio. So delta range 0 to 1. If I keep delta is equal to 0, what is your output? 0. Delta is 0.5. What is your output? Vs by 2. And then delta is 1. V out is equal to Vs. That's all. So that is your variations from 0 to Vs. So by varying the delta, you can able to get it from 0 to Vs. So that is your output voltage waveform variation. So by what I am doing? I am doing only continuous on and off regularly. If you do that, and how the variable delta, how it will be vary instead of this much duration, if you just turn on only this much duration, then turn off more duration, then what will happen? T on is less, no? When compared to total T is fixed one and on period is less, then that this portion is less. Instead of 1, you may get point 0.1, 0.2 like that. By controlling the on period, you will get it as a ratio control. Then automatically output is going to be controlled. That's it. So now when you compare to previous one, what are the previous ones? There is a what I call it as a resistance control, motor generator setup, then AC link chopper. So when I compared to that, this one is a very easy, no power loss, because switches are semiconductor switches, no. That's the reason the losses are very less, and you don't have any additional resistors and all to give anything to fire or something. It is all control strategy is very simple. That's why your average output voltage is going to be controlled without any losses. That's what. There is a chopper. Input is fixed one. Output is a variable one by using as a chopper. What is that chopper is inside this circuit. This circuit is nothing but a chopper. This one totally. But box consisting of the commutating elements L and C also. You need to design L value, C value at the time of commutation circuit, that will come into the picture. And now input is given constant and we are getting as output is like this. One full cycle you take it and integrate, you will get it as a variable voltage. That's what I drawn now. Output, input is Vs, and if it is on, output is same as the input. If it is off, output will be 0. So total time is T. You just integrate this, you will get it as the same as this. Now we will get it as a Vs into delta. Change the delta, we will get it as a variable voltage. If you keep delta is 1, you will get output is equal to input. Now here you will get less than the output is less than the input only for this circuit. Now you modify by adding some components and you try to get it as a step up chopper also. This I call it as a step down chopper or a basic chopper. So this is the basic of a chopper operation. And the T is a switching frequency. No, you just 1 by T is nothing but a F. You can write this output is like this also. V out is equal to F into T on by T on into Vs, because this variation T on into Vs by T, no, the T I can write as a F. That's all. The 1 by T is equal to F. So with this we can able to get it. Now there is a control strategies of a chopper also there, whereas in the case of control strategy means this one, no, how this what you call it as T on by T will vary, that is a control strategy. Whereas in the phase control rectifier, what you have, that is a alpha. R triggering, RC triggering, UJT triggering, RAM triggering, like that. We used some of the control strategies there. Now here control strategy is a delta. How the delta is going to be controlled by make use of this control strategy. They see that control strategies are two. One is a time ratio control, another one is a current limit control. So this is a time ratio control. This one is a current limit control. Again, time ratio is dividing as a constant frequency control and variable frequency control. Here frequency is a time duration, capital T. If we keep capital T is constant, that I call it as a constant frequency control. If I keep capital T is variable by varying that off duration or on duration without fixing the T constant, that I call it as a pulse width modulation, frequency modulation, that is a variable frequency case, and constant frequency case, pulse width modulation. So this is the control strategies of a chopper. Whether it is, you can say that any of the method, they have their drawbacks also, and I will explain that also. Time ratio control only preferably we can use it, but whenever you want to operate your machine, let it be as a DC machine, within a limits I want to operate, current limits. So what is the current limit? It should minimum limit as well as the maximum limit. You should don't want to vary that current in the motor within the minimum and maximum. Then only you can use as a this method, that is a current limit control method by minimum current as well as the maximum current limits. You can able to control the current limit control. So now we'll see briefly constant frequency control or a PWM control. What is the different? You can notice here the total time is this one. Both cases T is fixed. Here is the total time. Only variation is what? On duration. So if I keep on duration is this much, when comparatively total time delta, now it is a 25%. Delta is 0 to 100% or 0 to 1. Consider delta is 25% because on duration is only the 25% of the total time. Then I can say it is a 25% or 1 by 4th. You can say that 1 by 4th of T. Then I can represent the on period is equal to T on period is 1/4 of the total time. Then what I can represent? T on by T, that is equal to 1 by 4. 1 by 4 is a 25%. At same total time, see that what I did for the next case to vary the delta, my intention is to vary the delta only, that's all. Now if I do this T on period is this much, I got delta is 0.25. Suppose I want some more else 0.75, let us assume that. Then what I do? On period increases. Obviously off period will be reduced. Here off period is more and on period is less. But here on period is more, off period is less. Then what is the on period here? On period is equal to just 3 by 4th of the total period. Among the total period, 3/4 is or we can see 1 by 2 or something else. So only thing is from this we can notice that you can change the on period, automatically delta is going to be changed because formula itself it will show like that, no? Delta is equal to T on by T. This is formula. I am fixing the T constant. Then what is the thing? Delta is directly proportional to T on, no? I am fixed the T, so it won't change anything. So only one parameter is available to control the delta, that is the T on. So now you change the T on, proportionately delta going to change. This is a constant frequency. Why I call it as constant frequency? T fixed, no? Then frequency will be fixed. F is equal to 1 by T. So there T is fixed 1 for any value of delta. Then that's why I can say that delta is a variable one by changing the T on period, that is a constant frequency control. And then variable frequency control, what you will do is by changing the delta, you can see here, same formula only. But what I will do is this T on by T, no, T I will divide T on plus T off. Then what I will do, you keep T on fixed, where is the T off? Delta will change, then frequency also will change, or you fix the T off, you change the T on, then also delta will change, but frequency is going to be vary for each value of the delta. Now we can notice that variable frequency control case, variable frequency T on I am fixing the constant. See that first case, I am fixed the T on constant. This duration and this duration is same. On is constant. But how to vary the delta? By controlling the off. Here off period is small, here off period is more. Then the comparatively these two, delta is going to be vary, but time period is vary and frequency is vary. So this is the time period for the first case of delta and frequency is this much, but second case frequency varies. So every value of delta, frequency is going to be changed. That is the major problem if I use as a frequency modulation. And another problem you can notice here, otherwise also you can do, you fix the off period and on period you can vary. What I did first case, I fix the on period, I vary the off period. Second case, I fix the off period, I vary the on period. So if I fix this on period and vary the off period, some cases off period also large, that leads as a discontinuity current is going to be takes place. You know, that will come later. At moment, that is another problem, and this is another problem is frequency variation in every value of delta. The designing of filter also complicated if the frequency is not fixed one. So that is the some of the drawbacks in that. Then another one is a current limit control. What is the current limit control? The current should not go above the maximum level, motor current, and below the minimum level. So you should not operate the machine below I minimum. You should not operate the machine above I maximum. So that you can generate a firing pulses such a way that it should be in the within the limit. Now we can see this one is a firing pulses. Now if it reaches as a minimum and you can give the firing pulses, this let assume that it is a pulse and I am providing as a pulse. If I give the pulse, what will happen? Current will, because switch will be closed, this is circuit, no? There is a switch and then load, something like this is a switch. And switch is closed, what will happen? Current will be gradually rises, current will pass through that and current will be gradually rising. Once it reaches to the maximum, then what will happen? It reaches to the maximum current, then you disconnect the pulse. Otherwise what will happen? You continually on, this current will increase like this. But I don't want to allow the current beyond the maximum. Once current reaches to the maximum, you disconnect the pulse. That's why I switched off the pulse. Then what will happen? Current will not increase further. It is a dissipation. Current will be gradually decreases. And once it reaches to the minimum, then what? If I am not giving pulse next, what will happen? It will coming down like this. It is goes to the zero also. But I don't want to allow the motor current below minimum because it is a minimum, no? So it reaches minimum, you again give the pulse, then it will on. And once it reaches maximum, disconnect the pulse like this. So if you operate that on and off, so this is your within the limits. This is a minimum, this is a maximum. Again it is a minimum, it is a maximum. So with that you can able to get it your pulses continuously. You can get that average, or you can say that it never goes to as a discontinuous if you operate current limit control. So these are the some of the control strategies. So if you have any doubt, you can ask me. Then next controllers we'll see next time. Next class is there. And another classifications also, just will show this classification of choppers. As I mentioned, no, then this will end up the chopper introduction. Classifications of choppers, you can see voltage, based on the voltage level you can, and quadrant operation. So whether it is a higher voltage you need or lower voltage is need, that is one classification based on the voltage levels. Another classification is a quadrant operation. And voltage level, you can see that step down chopper. What is meaning of step down? Voltage will be, output voltage is a less than input voltage. And if you want higher the voltage also, step up chopper, because the chopper operation either depends on your requirement, either you go for higher voltages or a lower voltages. Another one is a step down and step up chopper, both is possible. So this is the based on the voltage levels you can classify step down chopper, step up chopper, up and down chopper. And quadrant, based on the quadrant, single quadrant chopper, two quadrant chopper and four quadrant chopper. So there is a chopper can operate only in the first quadrant or only in the second quadrant, that is category is a single quadrant chopper. And two quadrant chopper, that chopper can operate either first and second combinedly, first quadrant and second quadrant, that is one chopper. Another one is a first and fourth quadrant, so these are the two quadrant chopper. And all four quadrant also possible. So this is the classifications of a chopper. So that's what I mentioned. No, step down means output is less than input, and up means output is greater than the input, and both is possible in this. So these are the some of the classifications. And single quadrant we divide, type or class are same, either class A chopper or class B chopper. Class A chopper will give only first quadrant, class B chopper will give only the second quadrant. And two quadrant choppers are, two things are there, class C and class D. Class C chopper is a first and second quadrant.
Sir,
Class, yeah.
sir, time up, sir. Another class also started, sir. 11:30. We have another class.
Yeah, okay, ma, you can leave. Yeah, you can leave because I will take the attendance. I will download the attendance, no issue. You can join for the next class.